In this video, we're going to talk about open sentences and set builder notation. So we're first going to define what an open sentence is, or at least give a good model of it so you know what we're talking about. We'll show how open sentences are good for expressing rules. We're going to shift over to talk about what sets are. You've seen them before, but I just want to make sure we're clear about the language. And then we're going to define set builder notation using open sentences to define sets. All right, so let's get that. And then finally, of course, we're going to do some examples. All right, so let's look at the following sentence, which we've actually seen before. 2x plus 3 equals 9. And if you forget how that's a sentence, the 2x plus 3, that's our subject, equals is our verb, and 9 is our object. 2x plus 3 equals 9. So it is a sentence. It's a perfectly good sentence. The problem at the time was that it was not a statement. However, if we were to put in any number for x, it would be a statement. And literally any number, right? I could put in x equals 5. That gives me 2 times 5 plus 3 equals 9. Now, this isn't correct. I mean, this isn't true, but it is a statement. It just happens to be a false statement. And we can do that with literally any number. However, we could have problems if we put in something for x that is not a number. In that case, not a statement. So if I put in x equals chair or something like that, that's just a nonsensical sentence. It may give you a laugh, but it's certainly not a statement. So even though it's a sentence and it can be made into a statement by plugging in values of x, but we've got to be careful which values of x that we plug in there to make it a statement. And so this gives us a model for thinking about what is an open sentence, which, by the way, 2x plus 3 equals 9 is an example of an open sentence. And you can think of it as a variable statement, a statement with variables in it. So we can think of an open sentence as a sentence that would be a statement if not for some undefined variables in it. However, we should be cleared what we're allowed to substitute in for the variables. In other words, define what we were going to call the universal set. So we need the set of things that we can put in for our variables to make it a statement. All right, so here is actually an open sentence we've seen before. It hopefully will look familiar. X equals 2k for some integer k. Now, that looks a little bit familiar, of course, because that is the definition for what it means to be an even number. But it is an open sentence, right? So x should be some kind of number, right? It should be an integer or a rational number or a real number, right? We should be able to plug in a value of x and get a statement. And it turns out to be a rule for being an even integer, right? So for instance, if we put in x equals 3, we get 3 equals 2k for some integer k. There's no k that's going to make 3 equals 2 times k as long as we demand that k is an integer. But if we put something like 6 is equal to 2 times 3, so that won't be a true statement. So so odd integers will make the statement false, even integers will make the statement true. That is the rule for being an even integer. So the deal is that even integers make the sentence true. Other numbers, including non-integers, make the sentence false. So you can see now that open sentences are really good for situations where we want to make some kind of rule for some kind of concept. All right, so in particular, it's going to be useful for us to define sets, whatever those are. So again, let me give you a definition. A set is merely a collection of objects. And these objects can be abstract, like numbers. You can have sets of numbers. You could have sets of symbols. You can have something more concrete, like a set of chairs, like the set of chairs in my dining room or something like that. Or fences, the set of fences between myself and my neighbor's yard, something like that. And there are at least 2 ways that we can express a set. I should say 2 methods that we can use to define a set, right? So we can a set is a collection of objects. So one way we can do it is simply make a list of all the objects in a set. I'll call this the list model once we study sets more formally. And this is actually also called the roster model. There's 2 different ways of saying the same thing. This works well for a lot of sets. Like if you're looking for the set of chairs in my dining room, I don't have too many chairs, so you can list those pretty easily. But if you have infinite sets, like the real numbers or something like that, the list model it pretty much stinks. However, we can also use a different model that is much better for infinite sets. That is the rule model. And this is to make a rule that tells us precisely what items are in the set, so those are the ones that follow the rule, and what elements are not in the set, those are the ones that don't follow the rule. And as you've seen in the previous slides, what is useful for making rules? Well, open sentences. So we're gonna use that for some of the notation here. So as I mentioned, open sentences can help with this. So now that you've seen open sentences, now that we've properly defined sets, now that we've sort of explained the ways that we can define individual sets, now I think you're ready to think about set builder notation. So what set builder notation allows us to do is to define a set as a rule. And there are two things that we have to sort of set up our reader for this notation so they know exactly what's in the set. Part of it is sort of getting in the right frame of mind, and part of it is narrowing things down to the elements that we want to look at. Getting in the right frame of mind is tell us what kind of elements are in the set. If I'm looking for the set of chairs in my dining room, I want to be thinking about chairs. I don't want to be thinking about everything in the world, like numbers, like trees, like any other thing. I want to focus my attention on the things that matter. So tell us what kind of elements are in the set. And this is what's called our universal set. The universal set is the set of all things that I want to be thinking about as I'm defining this set. And then I also want to tell you, once you have that in your mind, tell us the rule that is satisfied by elements in the set. And that is going to be determined by an open sentence. Okay? So, two things. So the notation is going to look like this. Our set is going to equal the set of x in the universal set. In other words, x, we're telling x is like our random element that's going to be in our set, and it also has to be in this universal set to tell us what kind of elements we're looking at, such that x satisfies some rule, and that is going to be our open sentence. So let's look at an example. This is an example that really you don't need set builder notation for, because I don't have that many people in my immediate family. But yeah, let f be the set of people in my immediate family, and let's see if we can define this using set builder notation. So first of all, let's start thinking about what our universal set is. If I'm thinking about the set of people in my family, what sort of objects or entities should I be thinking about when I'm trying to think about what's in this set? Well, my universal set, it should be the set of all people. I should be thinking about people because people are in my family. Not all the people, but at least I should narrow down my attention to just thinking about people, so I know, okay, whatever this set is, it's going to have some people in it. And then I'm going to set my rule. And the rule is pretty straightforward. The rule is the person has to be in my immediate family. So first of all, I'm narrowing my attention just to people. And then among those people, I'm then using the rule to say I just want the people that are in my immediate family. So if I want to write this in set builder notation, here's what I'm going to do. First of all, my universal set is the set of all people, so I'm going to give that a name. Let P be the set of all people. So my set builder notation is going to say f is equal to the set of x and p. Remember, x has to be a person. I'm narrowing my attention to people, such that x is in my immediate family. X is in my immediate family. That's my open sentence. It is a sentence, and it is a statement if I put in a person for x. Any person. If I put a person in my immediate family, it's true. If I put in a person outside my immediate family, it's going to be false. Exactly what I want to define my set. So let's see, let's do one abstract example. So that's a concrete example, so you can see, people is very concrete. Let's do one with numbers. And so I want D to be the set of negative integers. And so again, I want to figure out two things. I want to figure out what am I talking about, what generally am I thinking about, what type of object, what's my universal set, and then what's the rule that those objects have to satisfy. So first narrowing of my attention is my universal set. I want to think of what am I thinking about? Well, I want the set of negative integers, so I'm thinking about integers, right? So what I want to do is I don't want to think about everything in my as a candidate for being in my set, just integers. So my universal set is the set of integers, and then what's the rule? Oh yeah. So remember the notation is that funny-looking z. What is the rule? Well, I want if someone gives me an integer, is it going to be in the set? I want to test to see if it's negative. How do I test to see if it's negative? Well, that integer has to be less than 0. So I'm going to narrow my attention to integers. Then I'm going to test to see whether each integer is less than 0. The ones that are less than 0 go in my set. The ones that aren't, don't. So my set builder notation is going to say D is going to be the set of all x and z, because again, z is my universal set, the set of integers, such that x is less than 0. It's an open sentence, right? X is less than 0. That's an open sentence. If I put in a value of x, it is either going to be true or false, depending on the value. All right, so I think you're ready to work on set builder notation yourself. There are actually two sets of activities. The first one's called set builder notation, which deals directly with set builder notation. The other is determining elements and sets. That one has sets defined in set builder notation, and then you figure out whether certain elements are in those sets. So anyway, those are on the 2 PDF files that are included with this video.